So currently, AI systems are in many ways very stupid. We are fooled into thinking they are smart because they can manipulate language very well. But they don't understand the physical world. They don't really have any persistent memory of the type that we have. They can't really reason and they can't plan. And those are essential characteristics of intelligent behavior. So one of the things that my colleagues and I have been working on at FAIR and at NYU actually is designing a new type of AI system, still based on deep learning, that would be capable of understanding the physical world, have persistent memory, be able to reason and plan. And in my opinion, once we succeed in building those systems around this blueprint, those systems will have emotions. So they'll have emotions like maybe fear or excitement or elation, because those are anticipations of outcome. Those systems will basically work by having a goal that we set them to fulfill. We'll give them goals to accomplish. And then they will try to figure out what kind of actions can I take so that I fulfill that goal. If they can predict in advance that this goal will be fulfilled, it will kind of make them happy, if you want, okay? Or if they predict that they can't, it will not make them happy. So to some extent, they will have emotions because they'll be able to anticipate the outcome of a sequence of actions they might take. But we will not hardwire into them anything like anger or or jealousy or anything like that, because
or consciousness. But consciousness
is something else. We don't know what it is really. There's no real
definition.
There's no definition of it. There's no kind of measurable thing really that can tell us whether something is consciousness or not. Like even if we observe animals, so we would probably all agree that apes and monkeys are conscious, and maybe elephants and maybe animals of that type.
That's what Roger Penrose said in our interview.
But is a dog conscious? Is a rat conscious?
Where is the barrier?
Conscious? Where is the barrier? Because we don't have a good definition for it, we really can't tell.
About the year, you said machine learning sucks. Was something changed?
We're working towards new ways of building machine learning systems so that they can learn as efficiently as humans and animals. Because currently it's not the case, okay? And I can tell you a little bit of the history of how machine learning has progressed over the last couple decades. So there's really three paradigms of machine learning. One is called supervised learning, which is the most classical one. And so the way you train a supervised learning system is that, let's say a system that is meant to recognize images. You show it a picture, let's say of a table, and you tell it this is a table. Okay, so it's supervised because you tell it what the correct answer is. The system computes its output, and if it says something else than table, then it's going to adjust its parameters, its internal structure, so that the output it produces gets closer to the output you want. Okay, and if you keep doing this, with lots of examples of tables and chairs and cars and cats and dogs, eventually the system will find a way to recognize every image you trained it on, but also images it's never seen that are similar to the one you trained it on. Okay, this is called a generalization ability. There's another paradigm which people thought was closer to the way animals and humans learn, called reinforcement learning. So in reinforcement learning, you don't tell the system what the correct answer is. You only tell it whether the answer it produced was good or bad. And to some extent, that can explain some type of human and animal learning. You try to ride a bike, and you don't know how to ride the bike, and after a while you fall, so you did something bad, and so you change your strategy a little bit, right? And eventually you learn how to ride a bike. Now it turns out reinforcement learning is extremely inefficient. It works really well if you want to train a system to play chess or play Go or poker or something like that, because you can have the system play millions and millions of games against itself and basically fine-tune itself. But it doesn't really work in the real world. If you want to train a car to drive itself, you're not going to do it with reinforcement learning. is going to crash thousands of times. If you're going to train a robot to learn how to grab things, reinforcement learning can be part of the solution, but it's not the complete answer. It's not sufficient. So there is a third form of learning called self-supervised learning. And this is what has enabled the recent progress in natural language understanding and chatbots. And in self-supervised learning, you don't train the system to accomplish any particular task. You just train it to basically capture the structure of its input. So the way this is used for text, for example, for language, is that you take a piece of text, you corrupt it in some way by, for example, removing some words, and then you train a big neural net to predict the words that are missing. Okay, a special case of this is that you take a piece of text, and the last word in that text is not visible, and so you train the system to predict the last word in that text. And this is the way large language models are trained on. Every chatbot is trained this way. Technically, it's a little different, but that's the basic principle. Okay, so that's called self-supervised learning. You don't train the system for a task, you just train it to learn the internal dependency of the input. And the success of this has been astonishing. It works amazingly well. You get systems in the end that seem to really understand language and be able to understand questions if you fine-tune them to answer questions properly using supervised learning or reinforcement learning. So this is what everybody has been working on in the industry, right? But that model does not work if you want a system to understand the physical world.
Something is missing.
Yes, it's just that the physical world is much more difficult to understand than language. We think of language as the epitome of intelligence because only humans can manipulate language. But it turns out language is simple. And it's simple because it's discrete. It's a sequence of discrete symbols. There's only a finite number of possible words in a dictionary. And so you can never train a system to exactly predict what word is going to come next, but you can train it to produce something like a score for every word in a dictionary or a probability for every word in a dictionary to appear at that location. And so you can handle the uncertainty in the prediction that way. But you cannot train a system to predict what's going to happen in a video. People have tried to do this. I've tried to do this for 20 years. And a lot of people have had this idea that if you could train a system to predict what's going to happen in a video, then that system will implicitly understand the underlying structure of the world, intuitive physics, everything that any animal and any of us as babies
All
learn.
physical rights.
Yeah, physical intuition. If that if I take an object and I let it go, it's going to fall. You've learned that gravity basically attracts every object towards the ground. Human babies learn this by the age of 9 months, roughly. It takes about 9 months to learn.
Maybe natural limitation of AI development today, it's our knowledge about the reality. We cannot replace more that we know. We have no idea how gravity was born. We have no idea how quantum world is transformed into classical one.
Yeah, but it's a simpler problem because your cat or your dog can learn about gravity in just a few months, right? And the cats are really, really good at this, right? I mean, they can plan complex actions and climb on all kinds of stuff and jump. So obviously they have a very good intuitive understanding of what we call intuitive physics. And we don't know how to reproduce this with computers yet. And the reason is, it's another example of what AI researchers have called the Moravec paradox. So Hans Moravec was a roboticist, and he made that point, like, how come we can have computers play chess and solve mathematical puzzles and things like this, but we can't get them to do physical things like manipulate objects that animals can do, or jump, or things like that. So it's another example of this paradox, that the space of discrete objects and symbols is easily manipulated by computers, but the real world is just too complicated yet. And the techniques that work in one case don't work in the other case. A good a good way to kind of visualize this, if you want, is that the amount of information that gets to us through our senses, let's say vision or touch, is absolutely enormous compared to the amount of information we can get through language. Okay, and this may explain why we have LLMs, chatbots. They can pass the bar exam, or they can solve mathematical problems, or write text that sound good. We still don't have domestic robots. We still don't have robots that can accomplish tasks that a cat or a dog can accomplish. We still don't have completely autonomous level 5 self-driving cars, and we certainly don't have self-driving cars that can train themselves to drive in about 20 hours of practice like any 17-year-old. So clearly we're missing something big, right? And what we're missing is how to train a system to understand complex sensory input like vision.
On your LinkedIn and Facebook, you are linking AI and entropy. What's the link?
It's been a bit of an obsession of mine. There's a big question which is at the root of a lot of problems in computer science, in physics, information theory, in a lot of different fields, which is the question of how you quantify information. Okay, how much information resides in a message? And the point I've made multiple times is that the amount of information in a message is not an absolute quantity, because it depends on the person interpreting this message. The amount of information you can extract from sensors, from a message language that someone tells you or whatever, depends on how you can interpret that. And so the idea that you can measure information in absolute term is probably false. Every measure of information is relative to a particular way of interpreting that information. So that's kind of the point I was making. And this has very far-ranging consequences, because if there is no absolute way of measuring information, that means there's a lot of notions in physics that don't really have kind of objective definitions, like entropy. So entropy is a measure of our ignorance of the state of a physical system. And of course, that depends on how much you know about the system. And so I've been sort of obsessed with this idea of trying to find good ways of defining entropy, complexity, or information content that is relative.